Hi everybody, this is Dr. Dado here to present crossover designs and now. Happy listening. This is the fourth in the series of my videos on design of experiment. Crossover designs and now is the topic of the present discussion. Irrespective of your versions of R, the reusable codes presented herein will run. Thank you. Assumption as usual that the bulk of, the theory part of crossover designs you already know. It's just mine is just to take you through the codes and tell you to explain them so that you can easily reuse them for your whatever work you intend to use them for. The reference material still remains Cochrane and Koch. Okay, about the data, but I need to say something about crossover design. Crossover design is particularly appropriate when the difference between the rows is substantially the same in all replications. Even if the difference between rows is known to be variable, crossover design may be preferable in small experiments where few degrees of freedom are available for error. When the number of treatments exists for seems to be large enough then, however, the degree of freedom for errors are sufficiently large so that a set of Latin squares is usually preferable. However, if it's less than, if it is 4 or below, you may do what is known as pairing, 4 choose 2, for effective comparison of how they will perform against each other. Okay. So, but otherwise, if it's larger than 4, well, you could do a Latin square. It is more preferable to use Latin square. In the present experiment, the data are times required to compute the sum of squares of 27 observations on each of 2 machines whose speed it was desired to compare. There are 2 machines, maybe one imported and then one locally made. We want to see, did they perform equally so that we stop importation of the foreign one and be using our local ones. Here it was suspected that the second machine is faster. Why? The second machine is probably the foreign one, the imported one. So for a fair comparison, each machine, the randomization process was placed on the choice of machine to use first. Why? Because you see weather fluctuations. If you are using the machine in the morning, the atmosphere will be cool, then such a machine is probably going to perform better than a machine that will be used much later when the temperature will have increased and the atmosphere will have been hotter. All right. So for fair comparison, each machine is to be used 5 times. But the randomization fashion is to check whether which one will be used first. All right. After the randomization process, it could be a flip of coin. When it comes head, it's machine A, otherwise it's machine B, sort of a thing. After the randomization process, this was the allocation that machine A be used at the first instance, third instance, the sixth, eighth, and ninth instances. Oh well. So this was the data that was obtained, comparing the speeds of computing machines. Those that are in sports will find this design very, very useful because you may want to check how your athletes are doing when you subject them to at least 2 different coaching techniques. How are they performing? This is the design for you. So although you're talking about machines, it very well could be individuals and things like that. Okay. So this is the data. And that's the summary of the tutor. All right. As usual, let's see what our manual computation will bring us. See, with manual computation, this was the ANOVA. The treatment, in this case, machines, significant, high, well, significant. All right. But we now come to the codes. If you give the codes, this code, this far to R, you will append it with the data. Here you are requesting ANOVA G, you are requesting for the ANOVA, and it will give you this. Now it's time to compare. You quickly go back and see whether you are on the same page with R. See, 3964, 320, 21. Let's see what the situation is there. 3964, 320, 21. Seems we are communicating. All right. And that's the respective probability. So again, don't be bothered about the row, don't be bothered about the column. Machine is what will be of concern to you. All right. Let's go to our linear model to see the situation of things. This is the code that will invoke the linear model. After that, you have the summary, and this will be displayed. And if you see, I had to say machine -1 so that it will display all machines. Both machines in this case. And it is telling us something here. It says there are statistically significant times and difference in times, both within and both between and within the machines. Since they are both within and between the machines. But with respect to the columns, no problem. No problem about the columns and the rows. So I said the machines, okay, just like the ANOVA is telling us anyway. But that's not enough. Remind it, we want to determine which machine is performing better. And how do we capture the one that is performing better? It will be how short their times are. The shorter the time for executing the same the same task, then the better. If one machine is executing the task with a smaller time, smaller period than the other machine, then that one that is performing in shorter period will be doomed to be better. So the visualization, this time around, you don't need the solution of any additional library. Just give this command to R. After getting here, give the command to R, and you will have this as the result. You see now? This is the situation with machine B, and that's the situation with machine D, telling us that our guess at the start was actually correct. Machine B performs better because the time for executing the task are shorter than that for A. Well, that's the farthest I intend to go with crossover design. Watch out for the competition of another design next time. Please like, share, and subscribe. Thanks for listening, and bye for now. Thank you. Bye, and remain blessed. Thank you.